The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
This morning's SciM News. Well, it's an article on something that's not totally up to date because it's a method that was developed 50 years ago called alternating direction. And it was exactly developed. First, you did an iteration in the x direction. Of course, we're tridiagonal along every row. We're one-dimensional. And then the second half step is an iteration in the y direction. Again, tridiagonal. So the iteration's very fast. You flip alternating direction, describes it perfectly. And that method is still used. It got developed in the oil reservoir simulation world. That is Houston. And the article says the evolution of techniques for oil reservoir simulation has continued. And then mentions three. So it went from this alternating direction to line over-relaxation, LSOR. Over-relaxation, and I only spoke briefly about that. What does that word line mean? It means that we're taking whole rows at once, working with blocks. And I'll add some notes about that today. So that was the next step, line SOR. Then to the Newton-Krylov schemes. That's what's coming. Krylov, conjugate gradients, with ILU type preconditioners. So again, we're talking about preconditioners, and one important choice is this incomplete LU. So notes on Gauss-Seidel, and I should maybe add incomplete LU. By the way, experiments badly needed here too, because incomplete LU has this tolerance, and as you move the tolerance, you get closer or far away to the exact L and U, but you get faster or slower. So what's the balance? What's the right tolerance? How do these methods compare? And overall, how do these iterative methods that we're speaking about compare with these direct methods? I mean, so we really are in this new chapter, solving large systems, facing a whole lot of possible new experiments. So just to continue the history or the future as described in SciM News, so there was alternating direction, line SOR, then to the Krylov schemes with ILU preconditioners in use today. So this is a big use area. And the multi-scale, multi-grid solvers that are, quote, now starting to come of age. So that's the third topic for today's lecture, multi-grid. That of course, it's been around for some time, but it involved, especially at the start, more programming, more effort in programming. And so it didn't quickly, I mean, it gave great results on model problems, on other problems too. But still, it kind of hasn't yet, but is penetrating into production code, where the oil reservoir industry or other big industries would use it. So here you see really a pretty fair picture of where we are today with large solvers. These are very important. Minimum degree, if the size is not overwhelming, direct methods are going to be right up there. And these are the pure iterations, stationary iterations, that with this idea, this incomplete LU idea, get pretty good. But the formula is always simple there. The new x comes from the old x by the same iteration. Whereas if we use the ideas there those, as preconditioners and look to see, so the point was, and I'll repeat it again, that Gauss-Seidel and Jacobi, the standard iterations, were quite satisfactory on high frequencies. They damp those out quite well in the error. But they don't tackle the low frequency, the smooth part of the error very efficiently. And that's what Multigrid does incredibly well. So that's it's a nice mixture of the two. These are the smoothers. This is the change of scale, change of grid that's coming now and will come. So all this will be my subject for this week and next prior to spring break. And I think you will have enough to go on to do experiments that could be highly interesting. Okay. So that's the SIAM News report. Okay. So what do I want to say about minimum degree? And more will go on the web. Just a few more notes about what we did on Monday after class. If you take a matrix like that, you take a matrix and how is it described in sparse format? Sparse format, you can see, normally you don't have to see it. It's usually inside the sparse MATLAB. But if you want to see what's happening, you could ask for I, J, and S. Now, what are those? What will that produce? I will be the list of non-zeros, the list of the row numbers of the non-zeros. So I will be, maybe I'll write it as a row, so I'm transposing. So the row numbers would be row 1, row 2, not row 3, row 1, 2, 3, row 2, 3. The column numbers would be, these are going to be the pairs, I, J. So that's column 1 twice, column 2 3 times, column 3 twice. And what's S? S is the actual numbers in those. In position I, J is the number 2. In position 2, 1 is the number -1. So those numbers, -1, 2, -1 is that column, and then -1, 2 is that column. So, of course, we've got all the information in the matrix. We know every non-zero position, and we know what that entry is. And, of course, our matrices are much bigger than this one. But already we can see one useful point. Point being the key word, that the column numbers, imagine we have a large matrix. So this J is not very efficiently recorded here, because what's J? We're looking at non-zeros column at a time. So, of course, we'll have a few 1s for the non-zeros in column 1, and then some 2s, and then some 3s, then some 4s. And but all we need, all this row is the real information in that row is a pointer to the. In other words, I don't have to repeat 2, 3 times. So really, if I put inside here a compressed version of J, a pointer would be a short vector that just has a 1 that says look in position 1 for the start of column 1, then a 3. See, I didn't need that, because that just continued column 1. That just repeated the J I already had. But this tells me that in the third position, I start down column 2. And this would tell me that in position number 4, 5, 6, I guess, I start down column 3. So you see the point of that 6. That 6 picks out, yes, 1, 2, 3, 4, 5. The sixth row number is the beginning of information on column 3. And then it's conventional to have a pointer 8 to say finished. So that's pointing to empty space, the first place. So in other words, J got compressed to 1, 3, 6, 8, and in a large problem it would get seriously compressed. Okay, so that's the form in which the code keeps the matrix and does the reorderings. Let me just mention that that the opposite of this would create the matrix out of these IJS. What command would that be? You could create the matrix A out of the command sparse would be good. Sparse of the inputs now would be IJS. If I input IJ and S, then MATLAB creates a matrix. I may want to, sometimes I may want to include the M and N, the shape of the matrix, as further parameters. But actually, here I wouldn't have to. So this is the opposite command from this one that we're interested in. Oh, okay, so just, you can imagine, suppose by using minimum degree or some other decision, I want to put I've eliminated up to a certain point, and I want to put the remaining columns in a different order. I can do that just by playing with the pointers. So it's a very efficient structure for sparse matrices. Okay. And then comes the question, okay, what's the good order? And I was surprised to realize how open a problem that still is, even from the expert who's developing the key codes for that. Okay, so it's so approximate minimum degree. Of course, by that word, you see that it allows freedom. There are also decisions to be made when the minimum degree is a tie between several nodes, as it commonly is. And you can, it's rather nice to get a MATLAB movie that shows the order in which nodes are eliminated, edges are removed from the graph, from the mesh. And you'll see that. Okay. All right, I'm ready to go ahead now to some comment on Gauss-Seidel. Maybe I'll put that here. In fact, maybe I'll just take the same matrix. So now I want to remember what is the Gauss-Seidel method for AX equal B. What's the iteration now? And again, A will be the same. 2, minus 1, 0, minus 1, 2, minus 1. My favorite. Okay. So all these iterations, you remember, are splittings of the matrix. Some of the matrix goes on the left-hand side. That's the preconditioner. So it's P, the preconditioner, that's sort of close to A in some sense, but easy to work with, multiplies the new thing. And on the other side is P minus A, the rest of the matrix that multiplies the old, plus the right-hand side B. Okay. And let's just remember again that if we converge to the point where this is the same as this, then we have the right answer. We have the right answer because if that's the same as that, PX is the same as PX, this comes over on the other side, AX equals B. So when it converges to the right answer. But you remember that the key equation was that the new error is the old error multiplied by this matrix I minus P inverse A. That's the iteration matrix, you could say. Yep, I just get it when I multiply both sides by P inverse. And so the problem is choose P so that this is easy to do, and at the same time, this has small eigenvalues, or as small as you can get. So the Gauss-Seidel is a particular choice which takes the lower, P is the lower triangular part here. So P is, so I just thought I better write down explicitly, Gauss-Seidel takes that with zeros there as multiplying, that's P. And what's P minus A? It's the rest. And it's been moved to the other side, so the rest is going to be the strictly upper triangular part. And because it's moved over to the other side, it'll have a plus sign. So it'll be 1 and 1. xk plus b. I just write it out so that you see totally explicitly how being triangular makes the solution step immediate. Because the first equation will tell us the first component, right? The first equation, because it's triangular, there's only an entry here. And by the way, all these codes, including Tim Davis's minimum degree codes, their very first step is reorder the equations if necessary to guarantee that the main diagonal has no zeros. We want to know that in advance. So that you just do, let's assume it, of course for us it happens automatically. Okay, so that's not zero. And that first equation gives us the first component. Then we know the first component, so we use it here. And then the second equation tells us what the second component is. We use that second component in the third equation to find the third component. And so there's no loss of speed compared to diagonal. And actually, it's faster because the storage, we're changing. We're using the new first component to find the second, and the new second component to find the third, so we can overwrite xk by xk plus 1. Okay. And let's see, if I had space and had prepared, I would figure out what this matrix is. Maybe you could do that. Figure out what here's P, it's invertible. P inverse is going to be quite simple. Actually, it'll be extremely simple, right? You'll be able to see its eigenvalues immediately. We could stop to do it, but I think if you do it, it's more valuable. So we would find that its eigenvalues were below 1, and that they were the squares of the Jacobi eigenvalues, and so the method is twice as fast as Jacobi. Okay, but it has the same good feature of damping the high frequencies and the same bad feature of not very much damping the low, smooth part of the error. Okay. So now we're ready for multigrid, which is intended to solve it. So multigrid is going to be, the point is, by changing grid, by changing from the fine grid to a coarse grid, the smooth oscillation doesn't look so smooth. On the coarse grid, its effective frequency is effectively doubled, and It's moving over in the direction where the smoother can attack it. We'll see that happen. Okay. So now I have to really, this begins the lecture on multigrid, which is going to take certainly today and Friday. And there's a very good book by Briggs and others. I'll just put, he wrote the first edition of the book and had co-authored the second one, and it's beautifully short and clear and simple, and this presentation will follow the same exposition that the book does. Okay. So the key idea is to see how to go from a fine grid problem. So this is on the fine grid with step size h. So this AH is our problem. It's our AH is A. AH, BH. We're looking for UH on the fine grid. Fine grid means lots of mesh points, lots of unknowns, big problem. Okay, so the idea is going to be somehow to, and let me just start with two grids. So the point will be, well, you can see what you do on the fine grid at the start. You iterate. You use Gauss-Seidel or Jacobi, whatever. Maybe 3 times. Maybe 3 iterations. But no, don't continue to 1,000 iterations. It's a waste of time. Okay, then here is the real, this is the multigrid part. So the multigrid part is going to, you get an answer after a few iterations, after you've smoothed it. You compute this residual, which is the amount you're wrong in the equation. It's the difference between the right side and the left side. I can put H's here too to emphasize this is residuals being computed with what we have, which is on the fine grid. Okay. Now here's the change of grid. Number 2 says restrict to a coarse grid. Take that RH, that residual, which is probably a bit smooth, right? And move it to the coarse grid. So the coarse grid we identify with by the fact that its mesh width is twice as big, 2H. And so we're going to need some restriction. So this, the input to this multigrid is to decide on a restriction matrix. How shall we take values that are given on a fine grid and restrict them to a coarse grid? Of course, one restriction is, and it's not that bad, is just to take the values of R that are on the coarse grid at every other grid point. Use those. Or we could take into account the neighbors. You see the question. We either, so this is coming now in this restriction. So the restriction is restriction R. This is fine to coarse. And we have this question of use neighbors or not. That will enter. Well, the decision on what the matrix R is. That's the key. Okay. So we choose an R, we restrict, and we have now a half size problem. Well, half size in 1D, quarter size in 2D, eighth size in 3D, because the mesh width has doubled in every coordinate. Okay, now I've put solve. I better put quotes around that. solve the problem on the coarse mesh. So the idea is that that's much faster. Well, you might say, what problem? Well, we have to create somehow the matrix on the coarse mesh. That's not necessarily given to us. We start the problem with AH, the matrix on the fine mesh. And can I just mention that this is probably, this V cycle, that letter V is supposed to suggest going down to the coarse mesh and back up to the fine mesh. And the standard notation in all the all the multigrid books is a capital V. And why do I use a small v? This is my educational contribution. Capital V is appropriate when you have several meshes. You go to 2H, you go to 4H, you go to 8H, back to 4H, back to 2H, back to H. So a deeper multigrid. So it would look more complicated. I would repeat this idea instead of solve here. Instead of solve at the 2H level, which of course I'm not going to do exactly anyway, but if I was in a big V cycle, I'd go on down to, I would iterate a few times to smooth here, just as I did here. I would iterate using weighted Jacobi or something, and then go down to the 4H mesh, so restrict to the 4H mesh. So you can see that I would stay in this little loop to get to the bottom, 8H, and then I would start back up. So I think it's a good idea to use a small letter V to tell us, rather than saying a 2-grid capital V cycle, I'm just going to use a small v to signal right away that it's 2 grids. Fine, coarse, fine. Okay. So we have some solution, not necessarily exact, and actually there isn't that much point in getting it exact. Because if we saw, what we want is to move toward the right answer. Okay. So, and notice that I'm looking here at the error rather than looking at A2H, U2H, the actual solution. What I'm computing with is the correction term. So this is the correction term that I find so this is the residual over here. This is the A2H that I still have to choose, and then solving that will give me a correction, but that correction is on the coarse mesh. I've only had that correction E2H defined on the 2H mesh. So now comes the other part of multigrid. Get back to the fine mesh. Climb back up. So I take that E2H and apply an interpolation. So that I need to create an interpolation. This is going to be coarse to fine. And I have to decide how to do that. Once I've decided it, that gives me a correction at the fine mesh level, which is where I'm really working. So I make the correction, and I have a better answer. And probably I iterate a few times. That would be called a post-smoother on that correction. And maybe that's where I stop. Or maybe I repeat little v cycles, but that's not brilliant. If you're going to do if you're going to repeat multigrid, it's much more efficient to move to more and more coarse meshes, because the calculations on these are way faster than on the fine mesh. Rather, you see, rather than if I much prefer to go way down and back up than a lot of V cycles. I mean, that would be a small W cycle and not brilliant. Much better to use a big V cycle or a big W cycle. There's a place for W cycles, but they're capital W cycles because you want to get down where it's very fast, very inexpensive, and in fact so efficient that Multigrid achieves this holy grail of giving you an answer with whatever accuracy you want, giving you an answer in O of n operations, n being the matrix size, capital N squared in our example. So that's the fantastic result from Multigrid. And so I'll come back to this, but just say it's if the size of A is n, which is capital N in 1D, capital N squared, capital N cubed, then the Multigrid works with in O of n flops, floating point operations. Not even log n, which we think of for the n log n, we think of for the FFT, for the fast Fourier transform. But here it's actually order of n. So that's that really is a goal worth achieving. Okay, so we know what the smoothers might be. It's the I and the R that are new. And then the analysis of convergence. Why does it converge? Okay. But to use the method, and so by the way, projects using Multigrid are totally welcome also. So let me take the interpolation I. So what's that? Coarse to fine. Let me imagine I'm in 1D. So there's the x direction. Here's one end of the interval. Here's the other end of the interval. And suppose my boundary conditions are 0. Okay. And then I have, so this is the coarse mesh. And let me put in here, make it the fine mesh. Okay. So the coarse, so at this point, I have an answer on the coarse mesh, so which satisfies the boundary condition, and let's say it's there, there, and there. Okay, and I need values on the fine mesh at the other points. Of course, I'm going to use these values when I interpolate. I mean, that word interpolation implies keep what you have on the given points. And I'm just going to do linear interpolation. So halfway there, and halfway there. Okay. So I'm inputting, ignoring the boundary conditions, the zeros. I'm in, it's going to be 1, 2, I have 5, it's going to be 5 by 2, I guess. This matrix I in this example will be 5 by 2. Because it has 2 inputs, these, and it has 5 outputs. And what's the matrix? Well, for the second and fourth outputs, it uses exactly the, so this is, right? This multiplies x, or I should say u, u1 and u2. Let me see if I'll follow the notes in. Now, the notes use v1 and v2 for the coarse mesh values. to avoid H2H extra subscript. So this height is V1, this height is V2, and I'm going to take, this will be the new U1, U3, and U5, and U2 I'm going to save. So this is, I better put make this into a true equation. IV, this is going to give me the values U1, U2, U3, U4, and U5. Okay. So U2 is just V1. U4 is just V2. No problem. That's what they want. And what do I do with the other ones? Let's see. I guess U1 is halfway between V1 and 0. Okay. So it's a half, right? U1 is just 1/2 V1. It doesn't involve V2. U3, which is sitting here, is half of these, so it's half of this and half of that, where this was nothing. Then U4 was the same as V2, just take V2. And what's U5? U5 is half of V2 and half of 0. So it's a simple matrix, the interpolation matrix. It's just reasonable to use the letter I, and we all recognize here it's a rectangular matrix, not the identity matrix. I doesn't stand for identity. Here it stands for interpolation. Okay, so there. I hope you can focus on that matrix. It just has, and if it was much, much bigger, but still in 1D, it wouldn't look very different. Each column would have 1/2, 1, 1/2. That's a typical part of the interpolation matrix. It uses the value V1, saves it at the center point, uses half of it at the previous point, and half of it at the right-hand point. And similarly, this you see it's sort of a a typical rectangular matrix in signal processing as well. Okay. I have to say something about what happens in 2D because our problems are in 2D. Maybe I just draw a typical 2D mesh. So these are the coarse values. This is the coarse mesh. And now and of course we'll save those values. I will have a 1, so it'll save those values when it goes to the fine mesh being half. So I just have to decide what to do there. So question mark. What value shall I take? Oh, I suppose I have to decide there too. These are all new points. And what shall I do? I'm just going to stay with linear interpolation, which is quite fast and satisfactory. This value will be the average of those two. This value will be the average of those. And what will this one be in the center? It's the average of these 4, of course. And that's what we'll get, actually, that Kronecker product business, the Kronecker product of a 1D matrix like that with itself would be a 2D interpolation that would do exactly this. We can write it out more fully, but it's not fun to write out really fully because if this is 5 by 2, then I2D would be 25 by 4. So we're right away, even on this tiny, tiny problem, we're right away up to 25 internal mesh points on the fine mesh. Okay. That's the matrix that I want you to see. And the natural choice for R is the transpose. So that one possible choice would, and the answer will be yes, we do use neighbors. So R will be the transpose of I. Actually, I'll need a factor here. I think it's 1/2. Let me just see what it is. Let me see what and why we need a little multiple there to make things right. But let me just, so there's my matrix I. So I'm just going to transpose it. And let me factor 1/2 out of that. Can I just, so you see these matrices without fractions inside, that would be 1, 2, 1. So I'm going to transpose that 1, 2, 1, 0, 0, 0, 0, 1, 2, 1. So I factored 1/2 out of I when I did that. And then I believe that I need another 1/2 here. I think I need 1/4. And what do I mean by needing 1/4? Of course, the main point is that this is the transpose of this. And you'll see that preserves the symmetry. That's just sort of the natural thing to pick. Not the only possibility, but it's very good to connect the restriction with the interpolation. Of course, you can't take the restriction to be the inverse of the interpolation. Why not? Why? I mean, that's sort of our mental idea is that the restriction goes in one direction and the interpolation in the other direction. So why not just let one be the inverse of the other? Well, of course, that matrix doesn't have an inverse. We lose. I mean, its rank is only 2. When we do a restriction, we're going to lose information. The interpolation can't put it all back because we threw it away when we restricted to the coarse mesh. Okay, now why 1/4? I think it's just if we had all constants like all ones as our mesh values, we would want to get all ones for the restriction. So if I multiply this matrix by the vector of all ones, so assuming you remember where R comes in, if I just copy this this equation, you remember that that I go from the H mesh, it's fine to coarse. So I start with so R times ones on the fine mesh, all ones on the fine mesh, gives ones on the coarse mesh. That's why I wanted that. You see, if I multiply by all ones, then that multiplication gives me a 1 plus 2 plus 1 equals 4, and I need to divide by 4 to get back to a 1. Yeah. So that you quickly discover that that just arises because of the change of scale. It's just a factor of 1/2. In 2D, that 1/2 there would change to 1/4. In 3D, it'd be 1/8. It's just the scaling to get back to preserve constants. Okay. And now the remaining question is what's A2H, right? That's the other matrix here that we're not given. We're given the AH, our problem. We choose an R and we choose an I, and if we're smart, one's the transpose of the other. And then the question is what's A2H? And there's a beautiful answer. So let me just say what it is. A2H, the coarse mesh matrix, is the fine mesh matrix, but I I need to do first, if this is going to apply to the coarse mesh guys, the V's, I have to do an interpolation. Oh, you see it here. This is 5 by 5 in my problem. So I need to first do the interpolation to get from a vector of length 2 up to a vector of length 5, then this, and then the restriction. It's terrific. That's A2H. So this is A2H. And we better do an example. And I guess it's going to be next time. So that'll be the first thing for next time, would be to see, okay, for the standard second difference AH, for these piecewise linear interpolation and restriction, what comes out as A2H? Do we get the standard second difference on the coarse mesh, which you really hope we do, and we do. Yeah. So this will be the second difference in our example on the coarse mesh. So that this middle step of multigrid is exactly what we would have expected, what we would have had if we'd set up the problem originally on the coarse mesh. But now we're going to get an answer that we take back to the fine mesh. Okay, so I'll do that next time. Some homeworks here that I held for an extra 2 days, and now I'm returning. And some thoughts to go up onto the website about possible projects, but actually I expressed a lot of them at the beginning of the lecture. Okay, thanks. Good.